All right, let's just jump right in. For more than 100 years now, physics has been dealing with, well, a ghost. It's this presence that haunts the subatomic world, a place that's so bizarre our normal rules just don't apply. We're talking about quantum mechanics, of course. And it all boils down to one simple but, man, incredibly tough question about what reality even is. So the mystery really comes down to this. What is light? And, by extension, what is anything made of? Is everything just a bunch of tiny little bullets, particles? Or is it all made of these spread out, continuous waves? For the longest time, everyone thought, well, it's got to be one or the other, right? Yeah, well, it turns out the universe is way, way weirder than we gave it credit for. The answer isn't A or B, it's somehow both. A single photon, a particle of light, can be a particle and a wave, sometimes at the exact same time. And the experiment that blew this whole thing wide open? Let's just say it's the scene of a major crime in the history of physics. So, welcome to our crime scene, the double slit experiment. Now, this thing has been around forever. The first version was done way back in 1801. But this simple little setup, it's the key that unlocks this whole quantum mess. This is the exact spot where our understanding of reality just shatters. The setup itself is so simple. Seriously, you've got something shooting out particles, let's say photons, and it shoots them out one by one. In front of that, there's a barrier with just two little slits in it. Then behind that, you've got a screen that basically lights up wherever a photon lands. That's it. So, what do you think should happen? I mean, if these photons are just little BBs, you'd expect two lines on the screen, right? One for each slit. Easy. But that is not what they saw. Not even close. What they got was this weird, stripy pattern, a classic interference pattern. And here's the thing, you only get that pattern when waves go through both slits at the same time and mess with each other. But hold on, we're firing them one at a time. How in the world can a single particle interfere with itself? It makes no sense. Okay, and this is where it goes from a mystery to a straight-up paradox. The scientists were just as confused as we are, so they decided to get clever. They figured, all right, let's put a little detector right by the slits so we can see which one the photon actually goes through. Simple enough, but the moment they did that, the entire result changed. Get this, the second you try to measure which slit the particle goes through, the very act of looking, the wave pattern just poof, it's gone. And you're left with those two simple bands you expected in the first place. It's almost like the particles know we're watching them, and they decide to stop acting weird. They snap out of being this wave of possibilities and become a simple little particle. And that's the famous observer effect. So, what on earth is going on? How do you even begin to explain that? Well, for the better part of a century, the main explanation, the one most physicists went with, was something called the Copenhagen interpretation. It came about back in the 1920s, and it was really the first serious attempt to make sense of this bizarre new reality. So the Copenhagen interpretation basically lays out a few core ideas, and they're pretty radical. First, it says the universe isn't a clockwork machine. At its heart, it's all about probabilities. Second, it says, look, if you can't measure it, you shouldn't even talk about it. And third, this is the big one, it says the act of measuring something is what causes the reality to happen. The particle doesn't have a definite position until we look. Our act of looking forces it to pick a spot. Now, you can imagine, this idea that reality is kind of fuzzy and only becomes real when we look at it, well, that didn't sit right with a lot of people. In fact, some of the biggest names in physics, guys like Albert Einstein and Erwin Schrödinger, they absolutely hated it. They felt like something was deeply, deeply wrong with this whole picture. Einstein's big problem with it is perfectly summed up in his famous quote, "God does not play dice." He just couldn't get behind the universe that was fundamentally random. He was convinced there had to be some deeper rules, something he called hidden variables that were really pulling the strings behind the scenes. And there was something else that really bugged him, a consequence of quantum mechanics that he famously called spooky action at a distance. We now call it quantum entanglement. It's this bizarre idea that you can link two particles together, and then no matter how far apart they are, even if they're on opposite sides of the galaxy, if you measure one, the other one is instantly affected. To Einstein, that seemed impossible. It looked like it was breaking the ultimate speed limit, the speed of light. And look, this wasn't just some quick academic squabble. This debate has been going on for over 100 years. It's been this long, drawn-out thing with all sorts of twists and turns. And funnily enough, in 1982,
An experiment by a physicist named Elaine Aspect actually proved that Einstein's spooky action was real. Entanglement is a real thing. Go figure.
To really drive home how weird this all was, Einstein's buddy, Erwin Schrödinger, came up with his famous thought experiment. You've probably heard of it, Schrödinger's cat. He said, imagine a cat in a box. In that box, there's also a tiny bit of radioactive material. If one of its atoms decays, which is a totally random quantum event, it triggers a mechanism that kills the cat. So according to the Copenhagen view, until you open that box to look, the atom is in a state of both decayed and not decayed at the same time. And if that's true, then the cat must be both alive and dead. So yeah, the whole zombie cat thing and the general weirdness of the Copenhagen view pushed other physicists to look for different answers. And one of the most popular alternatives is definitely the most sci-fi. It's called the many worlds interpretation. The many worlds idea is, well, it's bold. It says that wave of possibilities never actually collapses. Instead, every single time there's a quantum choice to be made, the universe itself splits. So with the cat, the universe splits in two. In one universe, the cat lives. In another, brand new parallel universe, the cat dies. There's no weird observer thing happening. There's just this constantly branching tree of realities. Now, as cool as that sounds, it's got a huge problem. It kind of breaks a fundamental rule in science called Occam's razor, which basically says the simplest explanation is usually the best one. And creating an infinite number of parallel universes just to explain why a tiny particle landed here instead of there, well, that is not simple. It's a massive, untestable price to pay. So if the Copenhagen theory is just philosophically bizarre and many worlds is just wildly extravagant, is that it? Are those our only choices? Well, no. There's another one. It's an underdog theory that was actually proposed in the exact same year as the Copenhagen interpretation, but it was pretty much ignored for decades. It's called the pilot wave theory. And really, the biggest difference between them all boils down to this one question. Is reality actually real, or is it just a bunch of probabilities until we measure it? Copenhagen says it's just probability, but pilot wave theory says no, everything is real and has a definite state from the very beginning. The observer isn't doing anything special, you're just measuring something that was already there. And the way this theory explains the double-slit experiment is actually beautiful. It says the particle is a real particle. It only goes through one slit, just like you'd think. But there's also a real physical wave, the pilot wave, that goes through both slits. That wave interferes with itself, creating this invisible pattern. And that pattern then guides the particle where to land. So the particle and the wave are both real, and they exist at the same time. Suddenly, there's no paradox. For decades, though, this was just a really clever idea on paper. There was no proof, no way to test it. That is, until the year 2011. The team of scientists came up with this incredible new method called weak measurement. Basically, it let them gently peek at what the photons were doing without completely disturbing them and collapsing the wave. And what they found was mind-blowing. The paths the photons took weren't random at all. They were following these very specific, strange-looking trajectories, the exact same trajectories that the pilot wave theory had predicted all those years ago. And just like that, all the weird paradoxes start to dissolve. The particle isn't a wave or a particle. It's a particle and a wave, together. The big, mysterious observer effect, turns out it's just our clunky measurement tools messing with that delicate pilot wave. Schrödinger's cat, it's either alive or it's dead, period, never both. And maybe best of all, the moon really is there when no one's looking. Reality, it feels real again. But this leaves us with one last, absolutely massive idea to chew on. For the pilot wave theory to work, that guiding wave has to be non-local. That's a fancy way of saying it has to contain information about, well, everything everywhere instantly. So what if every single particle in the universe is connected to every other particle through this invisible wave? It suggests a cosmos that isn't just a bunch of stuff floating in space, but one deeply connected system. A system where those connections might not just cross space, but time itself. So what is reality then? The riddle, it seems, is far from over.